Exercise 1. CPI cycle per instruction is a measure of the average number of clock cycles that a single instruction takes to execute. To calculate machine A CPI, we need to multiply the percentage of occurrence of each instruction category by the number of cycle per instruction for that category and then sum of the result. Here's the calculation. CPI equal by I will equal to 38 divided by 100 multiplied by 1 plus 15 divided by 100 multiplied by 3 plus 14 2 divided by 100 multiplied by 4 plus 5 divided by 100 multiplied by 5 equal to 2.85 MIPS million instructions per second is a measure of execution speed of a computer. To calculate machine A's MIPS, we need to divide the clock rate by the produce of CPI and 10 to the power of 6. Here's the calculation. MIPS equal to 200 megahertz divided by 2.85 multiplied by 10 to the power of 6 equal to 70.18 MIPS. Exercise 2. To calculate the MIPS rating for machine A and machine B, we need to first calculate the CPI for each machine and then use the formula MIPS equal to clock rate divided by CPI multiplied by 10 to the power of 6. For machine A, we have already calculated the CPI to be 2.85 in the previous response. So with a clock rate of 400 MHz, the MIPS rating for machine A is MIPS equal to 140.35 MIPS. For machine B, we can calculate CPI using the same method as for machine A. CPI is equal to 2.55, so clock rate of 400 MHz. The MIPS rating for machine B is equal to 156.86 MIPS. Exercise 3A. To determine which code sequence will execute faster according to MIPS, we need to calculate CPI and MIPS for each code sequence. For code sequence 1, we can calculate the CPI as following. CPI equal to 3.48 with a clock rate of 500 MHz. The MIPS for code sequence 1 is equal to MIPS for code sequence 1 is equal to 143.68 MIPS. For code sequence 2, we can calculate the CPI as following, and then it equal to 2.52 with a clock rate of 500 MHz. The MIPS for the code sequence 2 is MIPS equal to 198.41 MIPS. Exercise 3B, Puppy. To calculate the execution time of each code sequence, we need to divide the total number of instructions by the product of IPS and 10 to the power of 6. For each code, for code sequence 1, the execution time is equal to 0.00016 seconds. For the code sequence 2, the execution time is equal to 0.00015 seconds.
Okay, hello, my name is Nguyễn Quang Minh. My ID student is 13222 BI 13299. I'm going to tell you about the solution of the exercise number 4, exercise number 5, exercise number 6. So with the first solution of the exercise 4, we will have to determine which code subsequent is faster. We need to calculate the CPI for each code sequence. So for the first code sequence 1, we will have the equation to calculate the CPI as follows. On the screen you can see that, and when we substitute the number into the equation, we will have the result of it. The CPI, we have the result about 2.6, and with the following same way we do with the consequent 2, we will have the CPI or the consequent 2 is 2.25, and then we have the result of two different code sequence, so we can compare them, and we can see the difference in CPI between two code sequence is about 0.25. And then we move to the exercise 5. So in this exercise, we firstly to have to calculate the execution time for this program on for the stage with 1, 2, 4 and 8 processor. For B processor, the total number of instructions executed per processor is the equation of the arithmetic instruction is 2.56 to the power 9 divide 0.7 multiply with the P, and then we have the equation of load store instruction that 1.28 to the power 9 divide 0.7 multiply P, and finally we have the branch instruction is about 2.56 to the power 6, and then we will have the total number of clock circle required to execute the program on B processor is the equation clock circle that we will take the plus of all three equations before, and we will have the equation of the clock circle, and then we will have with a clock sequence a clock frequency of 2 GHz, the execution time for the program on B processor is the execution time equal to the clock circle divide 2 GHz. And then when we substitute the number into those equations, we will have the result of it, and for each value of B we will have 1, 2, 4 and 8, and we will have the result each execution time. With the one processor, the reason is 10.24 seconds. With the two processor is 5.49 seconds, and the four with the four processor the result is 3.06 seconds, and final is with the eight processor result is 1.76 seconds. The relative speed up of the two 4 and 8 processor result relative to the single processor results. With the speed up 2 processor, we take the execution time one processor divide to the execution time 2 processor, and the result will be 1.86. And with the same following, we have the result of the speed up processor for processor is 3.35, and the result of the edge processor is 5.72. Then if the CPI of the arithmetic instruction was double, it would increase the total number of clock cycles required to execute the program on any number of processor by a factor of clock cycle is 3 factor. So the only element we will double is the arithmetic instruction, and you guys can see the equation on the screen and the result of it. Then this factor is independent of the number of processor B, so the impact on the execution time of the program would be the same for any number of processor. So to calculate the value of the CPI of load and store instructions should be reduced in order for a single processor to match the performance of 4 processors using the original CPI value. We need to solve the following equation for x, and you guys can see the equation on the screen. And when we solve this equation for x, we get x the final result is about 3.03. So to match the performance of 4 processor using the original CPI value, the CPI of load and store instruction should be reduced about 3.03. And then we'll move to the solution of the exercise 6. So in this problem, the time it takes for an electric signal to travel from one edge of the chip to the other is equal to the diameter of the chip divided by the speed of signal. So you guys can see the equation on the screen, and the diameter, the result of diameter with in 1 nanosecond is 0.3 meter, and with the same following we have the result of diameter in 1 per second. About the result of it is 0.0003 meter. So a chip with a diameter of 0.3 meter or 0.0003 meter is technically feasible. However, there are many other factors that need to be considered when designing a chip, such as the power consumption, the heat dissipation, and the manufacturing costs. Okay, next will be the exercise number 7.
And to solve the seventh problem, I use the formula CPU time equals CPU clock cycle multiplied by clock cycle time. First, I calculate the CPU clock cycle of computer A using the given information. CPU time multiplied by clock rate equal 50 seconds multiplied by 500
multiplied by 10 power to 6 cycle per second and equal 2.5 multiplied by 10 power to 10 clock cycle. Next, I found the CPU clock cycle of machine B by multiplying the CPU clock cycle of computer A by 2.5 and I get CPU clock cycle of machine B is 6.25 times 10 power to 10 cycle. Finally, I use the formula clock rate equals CPU clock rate divided by CPU time to calculate the clock rate of machine B. Plugging in the value, we get clock rate of machine B equal 3125 multiplied by 10 power to 6 cycle per second and equal 3125 megahertz. Therefore, the answer to the question is that machine B must have clock rate of 3125 megahertz to run the program in 20 seconds. Then next, move to the next problem. For problem 8, I use the formula CPU time equal instruction count multiplied by CPI multiplied by clock cycle time. First, I calculate the CPU time of machine A using the given information. Instruction count multiplied by CPI multiplied by clock cycle time and equal 2 times 10 power to negative 7 times instruction count. By using the same formula, we get CPU time of machine B equal 1.625 times 10 power to negative 7 times instruction count. Then I divide the CPU time of machine A by CPU time of machine B to get the relative performance. CPU time of machine A divided CPU time of machine B equal 16 over 30. Since the ratio of the CPU time is greater than 1, so machine B is faster machine A and machine B is 1.23 times faster than machine A. And for the exercise 9, for the part A of exercise 9, first I calculate the performance of each processor by dividing its clock rate by its CPI. So I find that the performance of P1 equal 2 billion instructions per second and performance of P2 is 2.5 billion instructions per second and the last one is 1.82 billion instructions per second. So processor P2 has the highest performance expressed in instructions per second. And the part B, I calculate the number of cycles and instructions executed by each processor when running a program for 10 seconds. I use the formula CPU clock cycle equal execution time multiplied by clock rate equal and instruction count equal CPU clock cycle divided by CPI. For P1, I get 3 times 10 power to 10 cycle and 2 times 10 power to 10 instruction. For P2, I get 2.5 times 10 power to 10 cycle and 2.5 times 10 power to 10 instruction. For P3, I get 4 times 10 power to 10 cycle and 1.82 times 10 power to 10 instruction. For the last part of this exercise, I determine the required clock rate to reduce execution time by 30%. To do this, I increase the CPI by 20% and reduce the execution time by 30%. Then solve for the new clock rate using the formula. New clock rate equal instruction count times CPI time 1.2 divided by execution time time 0.7. I find that the required clock rate is 1.7 times the original clock rate, which means we need to increase the clock rate by 70% to achieve the desired reduction in execution time. So new clock rate of P1 equal 3.57 GHz and new clock rate of P2 is 3.57 GHz and new clock rate of P3 equal 2.61 GHz.
True. So let's start with the exercise 10. A this is a question about the computer architecture and performance. The global CPIs from Earth implementation can be calculated by talking the web uh, average of the CPIs uh, each class of instruction using the presentation using the uh, percentage of instruction in the first class as the west from P1 the global CPIs will be um, 0.1 0.1 multiply 1 plus 0.2 multiply 2 plus 0.5 plus plus 0.5 multiply 3 um, plus 0.2 multiply 3 equal 2.5 for P2 the global CPI will be would be 0.1 multiply 2 plus 0.2 multiply 2 plus 0.5 multiply 2 plus 0.2 multiply 2 is same 2. Yes, the clock cycle required from each uh, implementations can be calculated by multiplying the global CPIs by the dynam dynamic instruction counts of the programs from P1 the clock cycles required would be 2.5 multiply 1.0 E6 uh, equal 2.5 E6 for P2 the uh, clock cycle required would be 2 multiply 1.0 E6 equal 2 E6 in the B the size P2 has a lower number of
clock cycle require a high clock rate. It should be faster than P1 for these programs. Next is exercise 11. The average CPIs from Earth's programs can be calculated by dividing the uh, excursion times by the product for the dynamic instruction counts and the clock cycle times from the computer A. The advantage CPI would be 1.1 S 1.1 S divisions division 1 point is 1.E9 multiply 1 NS is equal 1.1 from computer B. The average CPI would be 1.5 S division uh, division yeah sure division 1.2 E9 multiply 1 NS is same 1.25. Yes. The B if the equation times on the two possession are the same then the ratio of cell clock rate would be equal to the inverse ratio of the average CPIS to the clock rate of the possession running computer A cost you would be 1.22 25 division 1.1 is the same 1 point 103 36. Yes, 36. Yes, time faster than the clock rate of the possession running computer because. And finally, C. Um, the speed up of using the new compiler version using compiler A or B on the original possession can be calculated by comparing the execution times of the new compile would be 6.0 E6 E8 multiply 1.1 multiply 1 NS is the same 0.66. Speed up visual using compare A would be 1.1 division 1 division 0.66 say equal 1.67. The speed up version using computer B would be 1.5 uh, division 0.66 equal 2.67. 27. So using the computer would, would result in the speed up of 1.67 times 67 times compared to using the computer A and the speed up of uh, 2.27 times compared to using computer B on the uh, re, Rhino processor. Yeah, sure.
Okay, so for this exercise, we have the CPI for arithmetic, load over store, run instruction, as well as the number of instruction per processor and the clock rate is 2 gigahertz. So we use the formula of execution time for processor, which is CPU clock cycle over clock rate, and the formula of CPU clock cycle, which equal the total of CPU clock cycle of arithmetic, load over store, and watch. So we can calculate the total number of clock cycle required for one processor, which is 18.176 multiplied by 10 to the power of 9, and the total execution time would be 9.088 seconds. So from two processors, we have to divide the number of instructions of arithmetic and load over store by 1.7 times of P, where P is the number of processor. So we can calculate the total number of clock cycle would be 10.112 multiplied by 10 to the power of 9. The total execution time would be 5.056 seconds. So the relative speed up compared to the single processor result would be 1.8. Similarly, we can calculate the total number of clock cycle and execution time for 4 processor and 8 processor, which are 3.328 seconds and 2.528 seconds respectively, and the speed up compared to the single processor of for 4 processor would be 2.73, and the relative speed up compared to the single processor result for 8 processor would be 3.59. So in the B part, right? So if the CPI of the arithmetic instruction was double, it would increase the total number of clock cycle required for each processor and increase the execution time of program on any number of processor. So, so for one processor, the total number of clock cycle would be 20.736 multiplied by 10 to the power of 9. The total execution time would be 10.368 seconds. The total execution time for two processor would be 5.696 seconds. And for four processor, the total execution time would be 3.712 seconds. And for 8 seconds, it would be 2.912 seconds. So we can see that it would increase the execution time of the program on any number of processor. This on to C part. This is a question about reducing the CPI upload of store instruction in order to improve the performance of a single processor, right? So from the previous calculation, we know that the total execution time for processor using the original CPI values is 3.328 seconds. So in order for a single processor to match this performance, its total execution time would also be 3.328 seconds. So let's denote the new CPI of load over store instruction as X. So, so we have the new CPI value uh, equation. So if we end the total execution time for single processor equation, so if we solve it for X, we will get X equals 6. So in order for a single processor to match the performance of four processor using the original CPI values, the CPI of load over store instruction must be reduced to 6. Okay, so in exercise 13, A part, this is a question about the performance of a new version of the AMD Barcelona processor. So to find new CPI, we need to know the number of instructions executed by the new version of processor. Since the number of instructions has been reduced by 15%, the new number of instructions would be 0.85 times the original of instruction. So let's denote the original number of instruction as n, the new number of instruction as new n. So we have new n will equal 0.85 times n, and the new CPU time would be 51.09 seconds. So the new CPI can be calculated by dividing the new CPI time by the products of the new clock rate, the new number of instructions. So the new CPI would be 15. Okay, so in B part, the increase CPI from part A is not similar to the increase in clock rate from 3 GHz to 4 GHz, and this is because CPI depends on various factors such as instruction set, architecture, microarchitecture, and memory energy, not just on clock rate. To calculate the in the C part, to calculate the reduction in CPU time, you need to know the original CPU time. However, this information is not provided in the question. So in D part, for only quantum benchmark with an executed time of 960 nanoseconds, CPI of 1.61, and clock rate of 2 GHz, we can use the formula execution time equal number of instructions multiplied by CPI over clock rate, and to calculate the number of instructions as n, we will use execution time multiplied by clock rate over CPU, which equal 1759 instructions. So if the execution time is reduced by an addition 10% without affecting the CPI, and with a clock rate of 4 GHz, the new execution time would be 864 nanoseconds. So, in E part, to give a further 10% reduction CPU time while maintaining the number of instructions, and with the CPI unchanged, need to know the original CPU times. However, this information is not provided in the question. Finally, for the F part, let's assume that the number of instructions is n and the original clock rate is x. So if the CPN is reduced by 50% and the CPU time by 20%, while the number of instructions is unchanged, then the new CPI would be 0.85 times of original CPI. New CPI CPU time would be 1.8 times of original CPU time. And, and if we use the formula of execution time, we will find the new clock rate, which uh, is 1.0625 times of the original clock rate. So if the CPI reduced by percent and the CPU times by 20% was the number of instructions the unchanged, then we need to increase the clock rate by a factor of approximately 1.0625. So that's all for exercise today.